In physics, the fundamental interactions are the interactions that do not appear to be reducible to more basic interactions. The four fundamental interactions recognized by modern physics are gravitation, electromagnetism, the weak interaction, and the strong interaction. The strong and weak interactions are described within the framework of quantum chromodynamics, while electromagnetism and gravitation are described through classical mechanics. Gravity is likely the most familiar interaction. Indeed, we can all experience its manifestation when throwing a ball, climbing a hill, or falling down. It is also causing the orbit of the planets around the Sun or the sphericity of most celestial bodies. More generally, the large-scale structure of the universe is determined by gravitation. Today, the theory of general relativity of Albert Einstein remains the most satisfactory explanation of gravity. Stated in 1915, it considers gravitation not as a force, but as a manifestation of the curvature of space-time under the effect of the energy of the matter in it. Newton's law of gravitation, developed at the end of the 17th century, remains an excellent approximation in non-relativistic cases, where velocities are low compared to the speed of light, and masses of the order of the solar mass or less. At the microscopic scale, gravitation is the weakest of the four fundamental interactions of physics, but becomes dominant as the scale increases and is acting at infinite range. Therefore, it is the most important of the four fundamental interactions for objects over astronomical distances. Interestingly, unlike the other interactions being sometimes attractive, sometimes repulsive, gravity always attracts, never repels, and nothing can cancel gravity. Merging general relativity and quantum mechanics into a more general theory of quantum gravity is an area of active research. It is assumed that gravitation is mediated by a massless particle called the graviton. Electromagnetic interaction includes the electrostatic force acting between charged particles at rest, and the combined effect of electric and magnetic forces. The electric component acts between charged particles, whether they're moving or stationary, creating a field by which the charges can influence each other. But once set into motion, those charged particles begin to display the second component, the magnetic force. The particles create a magnetic field around them as they move. With the gravitation, the electromagnetic force is one of the two interactions acting at infinite distance and responsible for virtually all the phenomena we encounter in everyday life above the nuclear scale. Basically, all the forces involved in the interactions between atoms can be explained by electromagnetic forces acting between the electrically charged atomic nuclei and the electrons of atoms. Therefore, the understanding of electromagnetism and its mathematical formalism by Maxwell in 1861 was of great importance. It explains the existence of electromagnetic waves, radio waves, light, microwaves, and gamma rays. The weak nuclear force is responsible for the radioactive decay of subatomic particles and is at the origin of nuclear fusion in stars. This is the literal change of one type of subatomic particle into another. So, for example, a neutrino that stays close to a neutron can turn the neutron into a proton, while the neutrino becomes an electron. It affects all known fermion categories, starting with electrons, quarks, and neutrinos. Its intensity is generally several orders of magnitude weaker than those of the electromagnetic and strong interactions, which explains its name. This interaction was first described in the 1930s by Enrico Fermi. Later, a description in the form of a very weak field was preferred, and in 1968, the electromagnetic and weak interactions were unified and presented as two aspects of the electroweak interaction. After the nucleus was discovered in 1908, it was clear that a new force, today known as the strong nuclear force, was needed to overcome the electrostatic repulsion of the positively charged protons. Otherwise, the nucleus could not exist. Moreover, the force had to be strong enough to squeeze the protons into a volume whose diameter is about 1 femtometer, much smaller than the entire atom. This force is the strongest of the four fundamental interactions. It is powerfully attracted between nucleons at distances of about 1 femtometer, but it rapidly decreases to insignificance at distances beyond about 2.5 femtometers. Once within range, massless charged bosons called gluons transmit the strong force between quarks and keep them glued together to make up protons and neutrons. A tiny fraction of the strong force called the residual strong force acts between protons and neutrons. Oddly, at distances less than 0.7 femtometer, the nuclear force becomes repulsive. This repulsive component is responsible for the physical size of nuclei, since the nucleons can come no closer than the force allows. The outstanding question of the four fundamental forces is whether they're actually manifestations of just a single great force of the universe. If so, each of them should be able to merge with the others, and there's already evidence that it may be the case.